Welcome back to Unraveling Human Physiology, where we try to make physiology easy for you to understand. Hi, today we are going to talk about renal clearance. Have you ever had performed some evaluation of your renal function and you have seen in your test something about creatinine clearance and you have wondered, what is this? To understand this, we have first to define what is clearance. Clearance is the plasma volume completely depleted of solute in the kidneys in a unit of time. But stop! First, I want to be really clear about the definition we have already stated, because it's really common that my students state that clearance is the mass of solute depleted by the kidney in a unit of time. But no, it isn't like this. Clearance is not about the mass of solute, but instead the volume of plasma, which is completely depleted of a solute in a unit of time. So I'll try to explain the concept in a more graphical way. So let's imagine that we have 200 milliliters of plasma with a solute which is like little balls. We have 12 balls of solute in 200 milliliters of plasma, and after this plasma have go through the kidney, it will suffer a clearance of the solute of 100 milliliters per hour. So if we have 200 milliliters and an hour have passed of clearance, we will have 100 milliliters devoid of any solute, empty, and the other 100 milliliters will be in equal concentration of solute as before. Does the plasma really look like this? 100 milliliters devoid of any solute and the other half in equal concentration as before? No, of course not. Because this plasma that we said that is devoid of any solute is what we called a virtual volume. It doesn't really exist. But we know that this is the quantity of plasma that has been depleted of solute in this unit of time. So how does the plasma really look like after being cleared of the solute? The remaining solute will be equally distributed in the 200 milliliters of plasma. To be even more graphic, I will replace the solute from little balls to a dye. So we have originally a dye in a certain concentration would give us a solution which is blue. After going through the kidneys, if I take a sample and see the solution, I will see that it's not anymore blue, but is light blue. That is the real thing. But if we want to calculate clearance of this solution, I will put in the bottom part of the container the solution in the concentration, the original concentration, so we can see the solution of blue. And in the above, we have the solution completely depleted of dye, so we see it white because it's empty. You see, it's not real, it's a virtual volume that we have calculated. So this part which is white, depleted completely of solute, this volume is the clearance of this dye. And in the bottom part, we have the part which is not cleared. So this is the difference between the real dye, which is the same the same color in all around the solution, that was the plasma will really look like with the dye depleted. But if we want to calculate which quantity of volume was depleted, we have to make the calculus like in the clearance with a virtual volume. I hope that now it will be more clear, the concept, it will be more easy to understand. I recommend you that you go on and see this definition several times, and it will be getting more clear each time that you will see again the definition, because it's a bit complicated definition. Don't feel bad if you don't understand quickly the definition. So now that you understand the definition of clearance, that's the tough part, we will go to a more easy part. How can we calculate clearance? The clearance of a substance X is the concentration of X in urine times the urine flux divided the concentration of X in plasma. So we need a urine sample, and usually it is a 24 hours urine sample, because clearance calculate from a 24 urine sample is more accurate. And then we need a blood sample. And now the next step. Why does doctors request creatinine clearance in particular? Creatinine forms part of the energy metabolism of muscle cells. When, for example, a part of these muscles are recycled, some creatinine is free and it goes to the plasma. When this plasma with creatinine reach the kidneys, and some creatinine will be filtered into the lumen of the nephrons. Once inside the nephron, creatinine doesn't interact with the nephron. It is not reabsorbed, nor did it secrete, so it will traverse all the nephron segments without change until it reaches urine, where it is eliminated. So the creatinine that is filtered is equal to the creatinine that is excreted. The mass of creatinine that is filtered is called the filtered load, and the mass of creatinine that is excreted is called the excreted load. To calculate the filtered load of creatinine, we have to do the concentration of plasma creatinine times the glomerular filtration rate or GFR. And to calculate the excreted load of creatinine, we need the concentration of creatinine in urine times the urine flux. As the excreted load and the filtered load are equal, I can rearrange the equation and put the concentration of plasma creatinine dividing the excreted load. So that gives us that the glomerular filtration rate is equal to the concentration of creatinine in urine times the urine flux divided the concentration of plasma creatinine. But look at this equation. It's the same equation of the clearance of creatinine. So here's an important key point. We can estimate the glomerular filtration rate by calculating the clearance of creatinine, and that's very useful. So, because we can evaluate renal function, in particular glomerular filtration renal function, by simply asking for a creatinine clearance of our patient. Very easy to do, non-invasive, very good way to estimate GFR. But look at this interesting point that is very useful in a shock room where we don't have 24 hours to estimate creatinine clearance. If we put aside the excreted load, we will have that GFR is proportional to 1 divided the concentration of plasma creatinine. This means that we can estimate GFR by simply looking to the creatinine plasma concentration. That's even more useful because we just run some blood labs, and we will see the creatinine concentration, and we can estimate if the kidney function is normal or not. But this is only the case if the concentration in creatinine is not rising because of other factors. So we can estimate GFR with plasma creatinine concentration, but if we want to be sure, we need to run some creatinine clearance. For example, if a patient who have never done some sport decide to go to the gym for 12 hours non-stop in a run, and then you perform some lab test. Probably if you look at the creatinine plasma level, it will be higher because some muscle cells will surely be lost and broken, and that will rise creatinine plasma. So you will be asking, plasma creatinine is high because the renal function is bad? But in this patient, if you in that time run a creatinine clearance, probably if the kidney function is normal, creatinine clearance will give you a normal creatinine clearance. And that's an example where creatinine plasma will not be a good estimator of GFR because it's high not because of malfunctioning of the kidney, but because of another reason, in this case, lysis of muscle cells. What happened with the clearance of a substance that is reabsorbed in the nephron? For example, sodium. Sodium, once it is filtered into the lumen of the nephron, when it goes through the different segments of the nephron, it will be little by little be reabsorbed. And then sodium in this urine will be very little. So when we calculate the clearance of sodium, it will be very little. The clearance of any substance that is reabsorbed will be less than the clearance of creatinine. Some examples of substances that are reabsorbed are glucose. Glucose is an extreme because clearance of glucose is normally 0, because in a patient which is with a normal functioning of glucose metabolism, none of this glucose will reach urine, so clearance will be 0. We have sodium. I told you that clearance of sodium is very little because most of it is reabsorbed. And then we have clearance of calcium and phosphate, which clearance will vary with the diet, with hormonal states, etc. And how's the clearance of a substance that is secreted? in the nephron. For example, we have paraminipurat. Paraminipurat is a substance which is filtered into the nephron, and you know that only 20% of the blood that is being filtered will be filtered, and the rest will remain and reach the veins. Before reaching the veins, the remaining paraminipurat will be secreted into the lumen of the nephron. So then the amount of paraminipurat will reach urine will be higher than the amount of paraminipurat that was filtered. And if we calculate paraminipurat clearance, its clearance will be higher than creatinine clearance. So for each clearance that is higher than creatinine clearance, this substance we know that it is secreted in the nephron. In particular, as paraminipurat is extremely secreted and none of the paraminipurat that reach the renal arteria will reach the renal vein, which the clearance of paraminipurat, we can calculate the renal plasma flow. Obviously, it's not a study that we perform a lot because we have to put an external substance into our patient, and sometimes we don't want to do that. But know that we can calculate, if we can estimate renal plasma flux if we need it. It's very simple. So now I hope that next time your doctor will ask you for a renal functioning test, and you will have a creatinine clearance test, you will know what that means. Thank you. If you like this video, please give me a like, subscribe to my channel, and activate your notification to know when my next video will be on. Thanks, bye!